So, hello everyone, I'm Sachin, and in this lecture, we will be calculating the spectral line shapes, which are embedded within your third order nonlinear optical response functions, which we shall calculate in this lecture under the use of a system bath model Hamiltonian, which I suppose I have introduced to you guys previously, so it's nothing new. And as a recap, in the previous lecture, we had calculated the third order polarization signal, and it was given by the convolution of these three electric field strengths and your third order nonlinear optical response function. So this one. And your response function had the following structure where the response function contained within it four so-called mini response functions, or the functions which account for your spectral signatures on your spectrum of the any specific third order technique. In this case, we are considering 2D spectroscopy, and so these contain the signals on your 2D spectrum, and they are your 4-point dipole correlation functions. As a recap, let us rewrite or jot down the structure of R1 through R4. And R1 takes on the following structure when you construct your coherence transfer pathway or your double-sided Feynman diagram, where your first interaction is on the ket side, second is on the bra side, third one is on the bra side, and the emission of the signal field is always from the left of the ket side. So you have your, you take a trace, and then you have your, let's say your equilibrium density operator, denoted by rho equilibrium or previously by rho 0. And then the first interaction acts on the ket side, so mu 0 acts from here. And then the last interaction also acts from the ket side, which is mu of T3 plus T2 plus T1. And then the other two interactions act from the bra side. So I will put that in a moment. And the other two interactions would be mu T1 and mu, let me reorder this as T1 plus T2 plus T3, and this as mu T1 plus T2. So as a recollection, the first light field here interacts with the ket side of the density operator. Then the second light field interacts with the bra side of the density operator given here. Then the third light field, which is the probe pulse, causes a stimulated emission or projects the population from a population state onto a coherent state. And that would be this dipole operator. And finally, the emission of the signal field, which is given here, would be accounted for by this dipole operator. Now we can rewrite this in the form of the 4-point dipole correlation function, which would be which would involve the movement of this term and this term towards the left, and then the trace of some quantity with the equilibrium density operator can just be written as the equilibrium correlation function of that specific quantity. So that's what I'm going to do here. So you get mu T1, mu T1 plus T2, dot dot dot, dot dot dot, mu T1 plus T2 plus T3, mu 0, equilibrium. Likewise, let us reconstruct R2. So this would contribute to your non-rephasing stimulated emission process, and R2 would contribute towards your rephasing stimulated emission process, but we are not discussing any of that right now. I would first like to construct the structure of these response functions, and then we can worry about which processes they are assigned to. So in the case of R2, contrary to R1, the first interaction is with the bra side of the density operator, and the second one is with the ket side. And then you get to a population state, and then you have your emission, and then the emission of the signal field. So it takes on this particular structure. So in this case, you write it as the trace, again of the equilibrium density operator, and in this case, from the from the ket side, you have mu T1 plus T2 plus T3, and then you have mu T1, and these two act on the ket side of the equilibrium density operator, and from the bra side, you have mu 0 and mu T1 plus T2. Right, again, so this would be equivalent to writing it in the form of the 4-point dipole correlation function. You have mu 0, mu T1 plus T2, mu T1 plus T2 plus T3, and then mu T1 equilibrium. And likewise, we can write R3 and R4 down too. So R3 takes down this sort of structure where your first interaction is with your bra side, and then your second interaction is with your bra side, then the third interaction is your ket side, and the emission of the signal field is also from your ket side. So again, this would be something like a rephasing stimulated emission. This would be a rephasing ground state bleach sort of process. Um, where you have a trace with mu T1 plus T2 plus T3 and mu T1 plus T2, and these are the interactions on the ket side of the equilibrium density operator, and on the bra side you have mu 0 and mu T1. Again, I will recast this in the form of the 4-point dipole correlation function. So you have mu 0, mu T1, mu T1 plus T2 plus T3, and mu T1 plus T2. And finally, you have R4, which takes on the following structure, where all the four interactions are with the ket side of the equilibrium density operator. So something like this, right? Where the emission of the signal field is given by this squiggly arrow. And that would be equal to the trace of the mu T1 plus T2 plus T3, mu T1 plus T2, you have mu T1, and then you have mu 0, and they all act on the ket side of the equilibrium density operator. And then this is equivalent to mu T1 plus T2 plus T3, mu T1 plus T2, mu T1, mu 0 equilibrium. Again, reminding you guys this rho equilibrium, previously I wrote it as rho 0. So they're both equivalent. So now we got to evaluate R1 through R4 using a system bath model Hamiltonian. So as a recollection, let us re-jot down the complete Hamiltonian. So our Hamiltonian had two components, which you can write down as the matter system Hamiltonian and some interaction with the light field of your matter system given by mu vector hat E of t, And in our case, we ignored the polarization of the transition dipole operator and the electric field. So in our case, we considered the simplified version where we wrote this as H0 minus mu hat times E of T. And your H0 is your matter system. So essentially, if you consider your sample, which I shall draw an illustration of here, and you have your incident light fields. Let's just say you have your two pump pulses and a probe pulse, which are separated in time, and they interact with this matter system. So within this matter system, you have chromophores, which can be either electronic or vibrational, or maybe some other degree of freedom, and they interact with a bath, which could include molecular vibrations in the case of electronic spectroscopy, or some other vibrational degrees of freedom which are not of interest in vibrational spectroscopy. So the molecular degrees of freedom in electronic spectroscopy will be treated as a bath, but in some cases in vibrational spectroscopy, the non-relevant vibrational degrees of freedom will also be treated as the bath and also includes solvent contributions. So you need to take care of these system bath interactions in our matter Hamiltonian of matter system. So your matter Hamiltonian is given by a system Hamiltonian plus a bath Hamiltonian and some system bath coupling between the two Hamiltonians, which is given by the third term. So under this framework, we will calculate our third order nonlinear optical response functions. So before we do so, let us consider a simpler case. So in the simpler case, let us go back to linear response theory. I suppose I have not introduced linear response theory previously, so there's nothing to go back to, but linear response theory would involve the perturbation of your sample with only one incident light field. So let's just say you have some sample and you have a single light field which perturbs this sample and then your signal is collected. So this would be an example of linear response theory would be UV visible spectroscopy, infrared spectroscopy, and so on and so forth, just with one light field. So like FTIR, UV vis would all contribute, would all classify as, would all be treated under the framework of linear response theory, essentially. So in linear response theory, you have only one light field. So your first order polarization would look very similar to your third order polarization, the structure, and we can easily extrapolate its structure from the third order polarization, which I have written above. So in this case, it would be 0 to infinity, dt1, e of t minus t1, and r t1, which would be your first order response. So in this case, the pulse is ordered such that you have an incident light field which interacts with your sample, and then your signal field is collected as a function of this T1. So that's what this means. And we calculate R1 to be written as mu T1 mu 0 minus mu 0 mu t1, or equivalently, it would just be the trace of the dipole operator at T1, dipole operator at 0, rho equilibrium minus trace of the dipole operator at 0, dipole operator at T1, rho equilibrium. Just a word of caution here that a lot of the times, which I shall be doing now too, this I upon H bar is considered within the structure of the response function, which I suppose I have not done previously, or have I? Yes. So this I upon H bar cube here can be brought down here and considered within the structure of the response function. So you can do the same thing here where you can bring this I upon H bar down to the calculation of the first order linear response. So to calculate these, in this case, you have 2-point dipole correlation functions. So to calculate these, we will use the same system bath model, and this is a simpler calculation as compared to the 4-point dipole correlation functions. So we start off with this. But just a quick heads up, this can also have a coherence transfer pathway sort of uh, illustration. So you can construct a double-sided Feynman diagram for this first order polarization too, which will help in your understanding. So I'm going to do that, where let's just say you have a ground state and you're probing some molecular excited state, call it E, and then you probe it. So in this case, your first interaction as shown here is with the get side of your density operator, bringing you to EG. And then your second light field also interacts from your, that this is the emission of your signal field. I apologize, there's only one light field which is at 0. And then your signal is collected as a function of this delay T1. And then the emission of your signal field at T1 is given here by this. So you go back to G. So this is how your dipole correlation function looks like. And then this is just the conjugate of this response function, making the response purely real because this I and a particular complex number, let's say A plus IB minus its conjugate, A minus IB will give you 2 times I. B, or this is just the imaginary part of that complex number Z, which is this. So this I helps in negating this I and makes the response of your system purely real. So just a quick digression, I apologize. And so you can have this sort of structure you can construct this coherence transfer pathway or double-sided Feynman diagram for linear response theory as well. And this further clarifies what this T1 is. So this T1 is the delay between the first light pulse being incident on your sample and the emission of your signal field. So this is the time at which your signal field is emitted. Right, so let us go ahead and calculate these 2-point dipole correlation functions, which are given by the trace of mu t1, mu 0 with the equilibrium density operator. So, as I previously described, your Hamiltonian matter system is given by your system Hamiltonian, your path Hamiltonian, and your system path Hamiltonian. So for your system path Hamiltonian, we will consider a simple two-level system with a ground electronic state and an excited electronic state. Needn't be electronic specifically, could be vibrational too. So I just call it a ground state and an excited state. And so in this particular basis of the system Hamiltonian, your the matrix representation would be diagonal, and the diagonal elements would carry the eigen energies of your ground state and your excited electronic state, which I would write this way with reference to the ground state energy. Right. And now let us write down your system bath coupling. So your system bath coupling will only have one entry, which is the fluctuation in transition energy of your excited state. So your system bath coupling in this case is diagonal, and you have the fluctuation in transition energies of your ground state and your excited electronic state, but then we write it with reference to the ground state. So again, you're only considering the fluctuation in transition energy of your excited electronic state in this case. And so in our very simplistic model, we assume that your system bath coupling only brings about fluctuation in transition energy of this specific transition, and the system bath coupling is not responsible for any other phenomena. And just as a word of caution, we also assume that the ground state and the excited electronic state are not coupled, and hence the light field is the only possible source to optically couple the ground and excited electronic state. So you need some sort of external energy, which is driven by these external light fields, and they bring about transitions or they couple the ground and excited electronic states. So those are the only way, that's the only way in which the ground and excited state can be coupled. I'm sorry, I keep on saying electronic, but this is more generic than electronic. So now let us go ahead and evaluate this two-point dipole correlation function, which is given by trace of mu t1. Okay, before I do that, I'm sorry. As I previously mentioned, this equilibrium density operator, which is given here, is the full equilibrium density operator. So it is the equilibrium density operator of the system states as well as the bath states. So I will write it in this tensor product or direct product notation because these are the density operator of the system states and the density operator of the bath state exists in different spaces, because your system space, or if you're considering your state vectors, your system state vectors are defined in a particular system Hilbert space, and your bath vectors are defined in another Hilbert space. So that's why you need to use this direct product or tensor product notation, because system and bath states exist in different Hilbert spaces, right? So that's why you write it in this direct product notation. Now, proceeding with our discussion, we assume that the system is in the ground state, and you can assign a specific distribution to your bath modes. So sum over nu, p nu, get nu, bra nu, where nu are states in the bath Hilbert space. So these states nu, they belong to, let me call it HB, which is the bath Hilbert space. And the probability of being in some state nu is given by a Boltzmann factor, exponential minus beta E nu, where E nu is the energy of that specific bath state, right? So this is your equilibrium density operator. And now we can proceed to calculate your two-point dipole correlation function. It's given by mu t1, mu 0, rho equilibrium, right? So this trace, which has to be now taken over all your system states and bath states. So you can first perform a trace over all your bath states. Take a trace over all your system states of this quantity. and then take a trace over your bath states, or you could take a trace over all your system states and then, sorry, take a trace over all your bath states first and then over all your system states of this specific quantity. And both operations should be equivalent as is governed by the property of the trace. So in this case, I would choose the first option. Now, the reasoning behind choosing this first option lies behind an approximation. So now, as is well known under the Born-Oppenheimer Heimer approximation, that the electronic and vibrational degrees of freedom, or in this case, your uh, system and path degrees of freedom. So this approximation holds much better in the case of electronic spectroscopy. So your system and path degrees of freedom are separated by timescales. So in the case of a very simple electronic transition, the when an electronic transition takes place, the electron density around the nuclear framework reorients itself very quickly relative to any changes in the nuclear framework. So in such a scenario, what you can do is you can assume that your dipole operators, which are given here, depend only on your nuclear coordinate. I will explain this a little bit better. So, from the Born-Oppenheimer approximation comes out the Condon approximation, which states that your dipole operator. Oh, I apologize for what I said. I just said that the dipole operator depends only on your nuclear coordinate. What I meant to say was the dipole operator is completely independent of your bath coordinates or your nuclear coordinates. I apologize for the mistake because it completely changes the meaning of this. So what I mean here is generally if your dipole operator depends on some bath coordinate, in this case, we approximate it to be independent of that path coordinate. And this is known as your Condon approximation, which somewhat stems from your Born-Oppenheimer approximation. So these two approximations are quite important to understand. So let us digress into that a little bit. So what does this Born-Oppenheimer approximation say? This Born-Oppenheimer approximation states that, in very simplistic terms, when you have a specific electronic transition, so this discussion, as I previously mentioned, is more suitable for electronic degrees of freedom. So, and as I previously mentioned, I am talking about electronic spectroscopy. So this would hold better in that context. So let me construct this diagram as function, as in this constructed with respect to some nuclear coordinate or vibrational mode coordinate Q, right? So let's just say I have some ground electronic state, and I'm assuming these surfaces to be harmonic. And then I have some excited electronic state. You don't really need to assume them to be harmonic. Let's say they're not harmonic for this case. But since we're doing the second order cumulant approximation and so on and so forth, the solutions would be exact for the harmonic approximation. But let's not worry about that right now. Let's just say you have a bunch of surfaces states on both these surfaces. And what this Born-Oppenheimer approximation says is when you have a specific electronic transition, so a transition from the ground electronic state to an excited electronic state, what happens when this electronic transition takes place is you have a reorientation of electron density around your nuclear coordinates. So let's just say you're considering some vibrational coordinate or some bond, and when you have an electronic transition, what happens is that this electron density reorients itself, but there is no change in your bond's length or your bond's coordinate. So this coordinate, let's just say, uh, reports on the length of a specific bond or something like that, right? So in that case, you have your particular transition, and it would be a vertical transition. because your coordinate does not change when you have this specific transition. So it would be a vertical transition. And what that would also imply is your dipole operator here, which we are considering, would not depend on this path coordinate q. And then the dipole operator is only a function of your ground and excited electronic state. I wouldn't say function, but you would write your dipole operator independent of your path coordinates or vibrational coordinates. So in this case, if you look really carefully, I make the Condon approximation now, and then these dipole operators, mu0 and mu t1, are independent of the path, as I just mentioned, or the path coordinates. So I can perform the trace over all the system states first, and then the dipole operators, which depend only on the system states, can be traced over the system states, and then the resultant trace can be performed over all the path states. So that would logically make more sense too. So we are going to do that now. And this approximation is known as the Condon approximation. So now what I'm going to do is I'm going to take a trace over all your system states first. So I'm going to take a trace over all your system states of mu t1, mu0, and firstly I would be taking a trace with your equilibrium system density operator, right? Because I'm operating in the system space first, and then that resultant expression can be taken as a trace with the path density operator, which is quite logical because this depends only on the system states and then this depends only on the path states. So quite logical. So let us do this trace first. As a final recollection, note this is approximated to be independent of path coordinates or states, right? So that's the Born-Oppenheimer approximation, or which leads down or boils down to the Condon approximation, which is incorporated here. So let's just take a trace over all your system states of mu t1, mu 0 with the system density operator, which is given by g, and then you're taking a trace over all your system states, which would include uh, bra g, the expression, get G plus bra E, the expression get E. And then since you have the get G bra G here, this term would vanish owing to the orthogonality of the two states. So the only term that is left is bra G, mu T1, mu 0, get G. And again, this is written in an interaction picture. So get bra G e raised to power I h0 t1 upon h bar mu e raised to power minus I h0 t1 upon h bar mu get g. And again, to redefine the structure of the dipole operator, you have mu eg get e bra g, and to assume the Hermitian nature of this operator, you have mu ge get g bra e, where mu eg and mu ge are conjugates of each other because the operator is Hermitian. And the diagonal terms are avoided because this is your transition dipole operator, and the transition dipole matrix elements are given by your off diagonal terms. So this mu acts on get G and causes a transition from G to E owing to this dipole operator term. So what you get firstly is mu Eg, and then you have the rest. Bra G, e raised to power I h0 t1 upon h bar mu e raised to power minus I h0 t1 upon h bar acting on get E. Now h0 acting on get E for now shall be written as I'm going to write it as h e acting on get E. Now, this needs to be understood a little bit carefully because this is the full matter Hamiltonian. Here I'm considering the full matter Hamiltonian, and what that means is that H0 has your system component, your bath component, and your system bath component. Right now, I'm acting only on the system states, but just know that your system bath Hamiltonian, which describes the coupling of the system with the bath, depends on system states as well as the bath states. So right now at this point, I would just like to use this as a marker. In this case, when I write it down as HE, I mean I'm considering the full Hamiltonian of the excited state E, which includes my system, my bath, and my system bath coupling. And I will take care of this later on. So let me just write it down that HE is the Hamiltonian of the excited state. It's still an operator. Note that. And then contains the energy of the excited state Hamiltonian coming from the system component, which is just h bar omega Eg. And of course, you have your bath Hamiltonian. And then you have your system bath coupling for that particular state E, which is just mu hat Eg, right? And then this mu hat Eg will again have to act on the bath states. So right now, and this is to recall, this is your fluctuation and transition energy of your excited state. So as of now, I'm just going to write it as this term e raised to power minus I H0 T1 as over H bar. I'll write it as e raised to power minus I He operator T1 upon H bar, right? So I will get mu Eg, and then I have e raised to power minus I H E T1 upon H bar. And then the second dipole operator brings the excited electronic state back to the ground state. And after that, you have, okay, so you will get a mu GE contribution from there. And I'm sorry, but I will have to arrange these terms well. So this will come here still. And then I will have this term, e raised power I H0 T1 upon H bar acting on ket G in that case. And then I will get e raised to power I H G T1 upon H bar. Right. And this is what I get from my first trace evaluation. And now the resultant expression has to be traced with respect to the bath state. So I get mu Eg, and then I trace this expression with respect to the bath states and the bath equilibrium density operator. So trace of bath, I have e raised power I Hg T1 upon H bar, e raised power minus I He T1 upon H bar, and then trace with respect to the bath equilibrium operator. So now I'm going to use this before I proceed, so it simplifies things, and then I will remove my system component from it. So here I'll get the e raised power minus I omega Eg T1 out, because all the evaluation with respect to the system states is complete. And from this case, as I previously mentioned, that the system component of the ground state is just zero, because I have written the energy of the excited state with respect to the energy of the ground state. So e raised power 0 will just give you a 1 here. So you get mu Eg, e raised power minus I omega Eg T1, and then a trace with respect to the bath states of e raised to the power how do I write this down now? Um, I would write it as e raised to the power I. It has your path operator and then your system path coupling. So I would like to find a better notation for this. So instead of going into the notational aspect of this, let's just evaluate these expressions, these time evolution operators given here. So if you consider this time evolution operator and this other time evolution operator, before I digress into this, I'm sorry, we'll have to take a step back because I missed out a specific point. So you have this, right? Trace over all the path states with your path equilibrium density operator, and this is e raised power I h g t1 over h bar e raised power minus I h e t1 upon h bar, trace over all your path states, and this is your uh, again an equilibrium correlation function with respect to all your path states of your the product of your two time evolution operators on your ground surface as such and your excited state surface, right? And now we want to evaluate these. So I did tell you that we can partition out the system component. So what you could do is e raised to the power minus IH. I'm going to use the notation alpha for now. So alpha in this case can correspond to G or E, or if you have a system which is more complicated than your two-level system, then alpha can refer to some other state as well. So let's just say I pull out the energy, the system energy of state alpha. So that would give you e raised power minus I omega alpha gt1. And then your bath and your system bath components are left here. So you have your Hamiltonian of your system, which would be h bar omega alpha g. Then you have your Hamiltonian of your bath and your Hamiltonian, your system bath Hamiltonian. Now, something which has to be noticed here, system path Hamiltonian as for that state alpha. So that would just be u hat alpha g, or your fluctuation and transition energy of that state alpha. So now just to know that this fluctuation and transition energy of state alpha explicitly depends on your bath Hamiltonian, because as the bath coordinates changes or the distribution of your bath states changes, your transition energy changes. So we have to rewrite this system bath coupling in the interaction picture with respect to the bath Hamiltonian. So what that means is that your fluctuation in transition energy, which is independent of time in the Schrodinger picture, gains some time dependence because of the path coordinates which fluctuate in time. So the way I would write this is I would write the system path Hamiltonian in the interaction picture with respect to the path Hamiltonian. So this path Hamiltonian does not have any time dependence, so I can just write this as e raised to power minus IHB d1 upon h bar, and then this can be written as a positive time-ordered exponential minus I upon h bar, integral from 0 to t1 u hat alpha g tau d tau. So this is how you can write the full time evolution operator of some arbitrary state alpha where you have some fluctuation in transition energy. And that's why the interaction picture is very important here, because This system path coupling depends on the path coordinates, and these path coordinates uh, change in time and causes the system path coupling to have some time dependence. And as a consequence of the system path coupling having some time dependence, it has to be treated in the interaction picture itself. So in this case, when you treat it in the interaction picture, you have this u hat alpha g tau, and then we are writing it in the interaction picture with respect to the path Hamiltonian. So you have e raised power I h b tau upon h bar mu alpha g e raised power minus I h b tau upon h bar. Yes. So the time dependence of this energy gap operator is given by these path Hamiltonians, these time evolution operators with respect to the path Hamiltonians. So now I will put that in here. And again, there is no system path coupling for this term. This term, as I mentioned previously, the ground state Hamiltonian does not have any system term or any system path coupling term. So it only has this common path Hamiltonian term. So what you get is e raised power I h b d1 upon h bar, which comes from here. And then from here you get the e raised power minus omega alpha gt1 can be taken out. Then you have e raised to the power minus ihb d1 upon h bar. So these two will cancel each other out. And then you have this term, this positive time ordered exponential term. So you write it as exponential positive minus I upon h bar 0 to t1 u hat alpha g tau tau, and then this is a trace for all your path states. It's an equilibrium expectation value, and then these two will cancel each other out. So for this specific part, you get the following expression: exponential positive minus I upon h bar 0 to t1 u hat alpha g tau tau, and then traced over all your path states. Right. So your expression as of now is equal to mu eg square exponential minus I omega eg p1 times this, and this is known as your line shape function, or also known as your dephasing function. Now, why is it known as the dephasing function? Because it dephases or causes decoherence of this coherence term. Because so this is just an oscillation, and then this will introduce some dephasing to this oscillation and is hence known as this dephasing term. So, and then you have this term. So now we want to evaluate this dephasing function. So how do we evaluate this dephasing function? As you recall, a positive time-ordered exponential can be expanded as such: identity minus, 1 minus I upon h bar 0 to t1 u hat alpha g tau d tau plus minus I upon h bar square 0 to t1 t tau 0 to tau t tau prime, it's for prime, u hat alpha g tau u hat alpha g tau prime dot, so on and so forth. So you have higher order terms as well. So what we are going to import, what we are going to use now is something which is known as the cumulant expansion technique. So, so how does this cumulant expansion work? So let's just say you have some observable A and you want to calculate the expectation of the exponential of that observable. So it can be written, so this is just some sort of ansatz, and then can be written in terms of the exponential of the cumulants of the particular operator. So n equal to 1 to infinity 1 upon n factorial kn, where kn is the nth cumulant of this operator or observable A. So this is what we intend on doing here too. We are trying to calculate the expectation of an exponentiated operator as the exponential of some cumulant of that operator. So that would help us a lot in our progress here. So this is what we are going to try to do. So we are going to use the second order cumulant approximation here. So we only consider cumulants up to second order of this operator A. So we use this, right, where we believe that the exponential of some operator A, the expectation of that can is equal to the exponential of the cumulants of that operator A. So you can take a ln of the expression on both sides. So before we do that, why don't we just go to the specific application which we're looking in this case, which is the positive time ordered exponential of this. Go to T1, you had alpha g tau d tau, and you make an ansatz that this is equal to exponential from n equal to 1 to infinity. I'm going to take 1 upon n factorial, and then I'm also going to do another thing where I write minus I upon each part to the power n. So you can do this or skip this, but I prefer taking the constant out and then we write it times k. And so kn is in this case the nth cumulant of u hat alpha g, right? So that's something which has to be considered carefully. And this is just a constant which I'm pulling out. You don't need to do that, but the result will still be equivalent. So nothing to worry about there. And then I take a ln on both sides of this expression. So I have ln of this term on the left, and it is equal to sum from n to infinity of 1 upon n factorial minus I upon h bar to the power n kn, where kn is the nth cumulant of the transition frequency fluctuation or the energy gap operator. So this quantity here, which is the uh, exponential positive minus I upon h bar 0 to t1, you had alpha g tau d tau, can be written as 1 plus sum from n equal to 1 to infinity, as we had previously discussed, minus I upon h bar to the power n. Previously, I'd put this as 0 and absorbed the 1 into the summation, but now I have taken that out. So the summation goes from 1 to infinity, minus I upon h bar to the power n, 0 to t, 1 here, t tau n, 0 to tau n, t tau n minus 1, 0 to tau 2, t tau 1 of, and then you have these energy gap operators, which are u hat alpha g tau n, so on and so forth, to u hat alpha g tau 1. And then you still have that expectation, or the you're calculating the ensemble average about all the Barth states, right? So you get this. And you know very well that ln 1 plus x can be approximated as x minus x square upon 2 plus x cube upon 3, blah, 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 blah. Taylor series, right? So yes. So, so this form ln 1 plus x can be written as x minus x square minus 2 and so on, so forth. And we can compare the cumulants on both sides to get a result, or what we can do is we can compare this coefficient minus I upon h bar on both sides and also get a result. So to calculate K1, which is the first cumulant on the right side, so please pay attention here. Oh, you have to consider n equal to 1. So you get minus I upon h bar times K1, which is the first cumulant. And from the left hand side, using the ln 1 plus x expression, you will only have to consider the n equal to 1 term from here. And I believe that you should get the first cumulant, which would be minus I upon h bar 0 to t1. Let me just call it d tau. And then you had alpha g tau traced over the path states. See, this comes off. And your first cumulant is given by this 0 to t1 d tau of, you had alpha g tau traced over all the path states. Now, you want to calculate the second cumulant. So K2, and here you have a 1 upon 2 factorial, and you have a minus I upon h bar square K2. Right. And on the left hand side, you will have two contributions now. One from n equal to 1 when it is squared, and of course from n equal to 2. So let's just write the n equal to 2 contribution, which will be very easy to see. You have minus I upon h bar square, and then 0 to t, let me call it d tau 2, 0 to tau 2, d tau 1. And then you have u hat alpha g tau 2, u hat alpha g tau 1 trace over the bath. Right. And now you have another contribution which will come from the first term minus I upon h bar 0 to, sorry, this is t1, this is to t1, to t1 d tau u hat alpha g tau. Right. Trace over all the bath states and you will square this term. Sorry, there'll be a minus 1 upon 2. So essentially, it's from here, coming from here, where the n equal to 1 term is squared. And this should also contribute to your cumulant, right? And then this, okay, let's just divide the minus I upon h bar square on both sides. So this cancels this and then this. So that's why I put in the minus I h upon h minus I upon h bar on the right hand side. It enables for easy cancellation, but you can still work without cancelling the minus I upon h bar, right? So this gives you from above the first cumulant, K1, and you multiply both sides of the equation with 1 upon with 2 factorial. So your second cumulant is 2 factorial or 2, so right, 2 times 0 to t1 d tau 2, 0 to tau 2 d tau 1, u hat alpha g tau 2, u hat alpha g tau 1 raised over the bath minus k1. And likewise, you can generate the third order cumulant, the fourth order cumulant, the fifth order cumulant, blah, 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 blah. So you can define these cumulants as such, and they are very easy to think about. So now we go back to this uh, part here, and we wrote the expectation of the positive uh, time ordered exponential here as the exponential of the cumulants. So what you get now is the exponential minus I upon h bar 0 to t1. You had alpha g tau t tau is equal to exponential sum over n 1 upon n factorial minus I upon h bar to the power n times kn. Now we need to study something important. This mean or the average fluctuation in transition energy here, you had alpha g is taken to be 0. So you had alpha g is assumed to be 0. Now this just comes from the approximation that this transition frequency fluctuation or transition energy fluctuation of a particular transition follows a Gaussian distribution. So if I write omega alpha g, this is the average fluctuation in transition energy. And no, sorry, this is the average transition energy. So this is the transition energy distribution of the ensemble, and then this is the average transition energy of the ensemble. So if I take an ensemble average of the fluctuation in transition energies, it should be equal to 0. So the entire idea behind this approximation that your transition frequencies or your transition energies follows a Gaussian distribution follows from the central limit theorem, in a sense that you have multiple path molecules or essentially a system interacting with a lot of uh, instances of the environment and a lot of path molecules in this case, or coupled to a large degree of vibrational modes. And as a consequence of that, it is assumed that your transition frequency distribution follows a Gaussian distribution. And this follows, as I previously repeated, from the central limit theorem in calculus. Not calculus, in statistics, I apologize. So if you assume its validity, your transition frequencies follow a Gaussian distribution, and as a consequence of which, to fully characterize these transition frequency distributions, you only need to consider the first moment, which is the mean, which is considered to be 0 in this case, and the second moment. So we only need to consider the two moments, and then you assume that the higher order terms, they will vanish. So the third order cumulant, the fourth order cumulant, so on and so forth, they will vanish. So only you consider the first cumulant and the second cumulant, which is here. And as I mentioned, since this mean is 0, we approximate this as 0 because this is assumed approximated as 0. And hence K2 is equal to just 2 times this term, and this K1 cumulant is assumed to be 0, right? So here we will only have n equal to 2 contribution, and you can write it as 1 upon 2 factorial minus I upon h bar square times K2, which is 2 times this term above. So this 2 and 2 will cancel each other out, and you get minus I upon h bar squared integral from 0 to t1 d tau 2. Okay, let's not use d tau 2, we'll just use d tau and d tau prime instead of d tau 2 and d tau 1 henceforth. So d tau 0 to tau d tau prime, and you have this is all in the exponential. So yes, have you had alpha g tau, you had g. So this is what you get as an approximate answer after using a second order cumulant approximation to your dephasing function, which is given as follows: 0 to t1, uh, you had alpha g tau tau, and this is also an average with the bar. So this would just give you minus 1 upon h bar square. So now you can jot down your full solution under the second order cumulant approximation for your linear response function. So your 2-point dipole correlation function is approximately written as the product of your oscillator strength, your coherence times this exponential minus 1 upon h bar square, 0 to t1, t tau, 0 to tau, t tau prime. You had alpha g tau, you had alpha g tau prime traced over the path. And so this is your final expression. Now, this 2-point dipole correlation function over all the path states is known as, uh, in this case, it is known as something, what is the FFCF? It is known as the frequency fluctuation correlation function. So what it does is it correlates the transition frequency fluctuations of a single transition. So this is alpha g at two different times t and t tau and tau prime. So it is just uh, it can be written as tau minus tau prime using the properties of the correlation function. But as I previously mentioned, these are energy gap operators. So you divide each energy gap operator by h bar, and then you get the fluctuation in transition energy. So what I mean is 1 upon h bar square, you had alpha g tau, you had alpha g tau prime, is known as the FFCF, or the frequency fluctuation correlation function, denoted by C alpha alpha tau minus tau prime, because this can be written as you had alpha g tau minus tau prime, you had alpha g 0. Because these correlation functions are simply functions of the interval between these two time arguments, right? So also you can use that to simplify this integral a little bit, where if you do that, you get the term there as exponential minus 1 upon h bar square, 0 to t1, t tau, 0 to tau, t tau prime. You guys should try this out, and then can be written as you had alpha g uh, tau prime, you had alpha g 0 trace over the path. So it can be rewritten in this way as compared to the way it is written where there's tau and tau prime. So it can just be written in terms of tau prime. And then that tau prime is integrated from 0 to tau. And then the resultant contribution is integrated from 0 to t1, right? So, but that was not my point of discussion here. So this C alpha alpha, let me just use some generic index T for simplicity. is given as 1 upon h bar square. You had alpha g t. You had alpha g0 trace over all the path states. So you had alpha g upon h bar is just, so this has units of energy, and divided by h bar you can write it as delta omega alpha g. Why is delta omega alpha g? Because now you're tracking the transition frequency fluctuations instead of the transition energy fluctuations. So some people write this as delta omega alpha g at time t, delta omega alpha g at time 0. Right. And this is known as your FFCF, or frequency fluctuation correlation function. Now, if I integrate this frequency fluctuation correlation function twice, as shown here by this, it gives me something which is known as the line shape function. So I will define G alpha alpha t as the double integral, so 0 to t of d tau, 0 to tau, d tau prime of C alpha alpha tau prime, or 1 upon h. Okay, let me just write it in terms of the delta omega. Delta omega alpha g tau prime, delta omega alpha g 0. So this will be called your line shape function, or just to make sure that you guys are not confused from the previous definition of the line shape function, uh, we will just call this the dephasing function. So it makes things a little bit more simpler. So the complete expression is known as the dephasing function. And once you do your second order cumulant approximation, what you get is, here you get exponential times something, and then that exponential times something, that times something is your line shape function. Okay, it's not too clear right now. Let me rewrite this again. So you had t1, you had 0 is equal to mu eg square exponential minus I omega eg t1 times exponential of this quantity minus times this quantity which I have pulled down here, and it is left as an exercise for the viewer to prove that this quantity which is highlighted in pink is equivalent to this quantity which is highlighted in red, where the correlation function just depends on one time argument, and here it's dependent on two time arguments, and that can be proved using this property that you have your correlation function with these two time arguments, and then it can be recast as follows. So the proof is left as an exercise, and so you get exponential, and then you have a minus from above, and then you have this term, and then this term integrated twice gives you the line shape function g alpha alpha t1, and then this we will define as the line shape function. So the entire thing exponential minus this thing is the dephasing function, and then this dephasing function was calculated, just to recall, under the second order cumulant approximation framework. Okay. And then this line shape function is generated by a double integration of your correlation function. or your frequency correlation function known as your FFCF. And then this FFCF correlates your transition frequency fluctuations at time zero to some other time tau prime. 1 upon h bar d tau. So this goes from 0 to t, 0 to tau, d tau prime. You can use any integration variables as such. And C alpha alpha tau prime, where C alpha alpha tau prime is your FFCF, or your frequency fluctuation correlation function. And that's what contains your 1 upon h bar square. So I'm sorry, I shouldn't mention this here. And then this C alpha, this correlation function is 1 upon h bar square delta, sorry, this one have u hat alpha g tau prime u hat alpha g 0. Let's hope I haven't made any mistake anywhere with the 1 upon h bars. No, I haven't. And then this is equivalent to writing it as delta omega alpha g at tau prime delta omega alpha g at time 0. So I hope this is clear. So your 2-point dipole correlation function calculates as follows. Now you need to realize that your response function are as a function of t1, which is your first order response function. Let me go all the way back to the top. The thing which we were initially intending on calculating, which is given by I upon h bar times the two-point dipole correlation functions, which are just conjugates of each other, is given as I upon h bar times this quantity minus its complex conjugate. So this is a real quantity, this is a real quantity. So you don't have to worry about these two, they can just be pulled out. So you get mu Eg square e raised power minus g alpha alpha. Oh shit, I'm sorry. Now you do not have the alphas anymore. So the alpha thing which I had introduced for simplicity refers to the energy state E. Let me go back up here. So I had introduced this alpha, but this alpha was just for notational simplicity, and in this case, this alpha corresponded to the excited state E. So everywhere I had used mu hat alpha g, I should use u hat eg now. So I apologize for that. So it would be g e e t1, which makes sense. And till here, these alphas were just generic notations. And along with that, you have the e raised to the power minus omega egt1 minus its complex conjugate, which will be positive I omega egt1. So this will give you minus 2i times sine omega egt1, and that will give you 2 upon h bar mu eg square times sine omega eg d1 times the exponential minus GEE d1. And then this is your first order response function. And using this, you can calculate your first order polarization for some finite electric field width. But if you assume that your electric fields are infinitely narrow in time or temporally infinitely narrow, your response function here is approximated as your linear spectrum. But then this is again assuming that your electric fields are infinitely narrow, or the impulsive limit approximation, which we haven't discussed yet. So we will stop at this point in this lecture. And in the next lecture, we will be calculating the third order nonlinear optical response functions, which I had gone over at the beginning of the lecture. So I mean R1 through R4. We will evaluate it using the same second order cumulant approximation technique. So the entire idea behind this evaluation and considering linear response theory was to introduce the second order cumulant approximation to you guys. And in the framework of linear response theory, we only had a 2-point dipole correlation function. So we simply had to evaluate these sort of structures to calculate your response. Now, in the next case, we will have to evaluate 4-point dipole correlation functions. Something like this. Apologize the swap of the T1 and T2. So in previously I had written T1 plus T2 plus T3. Now I'm writing T3 plus T2 plus T1. They're the same. This is R4 corresponding to the non-rephasing ground state breach, but then you have R1, R2, R3, 2, and we will evaluate these using the second order cumulant approximation technique, which I have introduced you to in this lecture. So we will proceed from here in the next lecture.